Problem set 2.9, number 6. Determine the magnitude of the acceleration of each block and the tension of the cord for each scenario. The pulley connected to M2 can move. So M2 is connected to this pulley. So assuming M1 moves this way, then this cord will go that direction, lengthening this space. So M2 can move. Scenario 1, mass 1 is 6 kilograms and mass 2 is 10 kilograms. Coefficient of static friction between M1 and the table is 0.9 and the kinetic friction is 0.4. All right, so the first thing, just going into this, first question I have is this even going to move at all? Since I'm given the coefficient of static friction, that implies that maybe it doesn't move. And so there's going to be some tension on this block due to this rope, of course, due to that mass pulling down. So this tension here is going to pull on this block, but the friction is going to resist its motion. So I think what I need to figure out is how much tension is going to be in the rope and how much static friction could there possibly be. And I should compare those, because if the tension is less than the static friction force, then it won't move, because the tension just won't be strong enough to break the friction. So let's find out. That's our first question, just a yes or no. Is friction big enough to make this thing move? Well, before I get to that, let's figure out what the tension is. Let's assume for the moment that it's not moving. So that means that M2 has I'm gonna call it M2G is down like that, and there are two tensions upward. There's two ropes upward on that object, and if it's at rest, then 2T equals M2G, and I already know that the mass of that is 10 kilograms, so 2T equals 100 newtons. Tension is going to be 50 newtons. All right, so let's bring that over to the second, first M1. M1 is going to have tension to the left, and let's assume or consider static friction to the right. Now it's sitting on the surface, so there's also M1G down and normal force up. So the question, tension question mark, greater or less than static friction? Well, static friction has a maximum value of mu static times the normal force, and because the normal force in this case minus mg equals 0, the normal force equals mg, so plug that in there. So the friction, static friction maximum would be 0.9 times, is it 6 kilograms times 10, so it's 0.9 times 60. 0.9 times 60 is 54 newtons. That tells us that the maximum possible static friction that could exist on that block is 54 newtons, which is greater than tension. Therefore, it is not even going to start moving in the first place. There is enough friction here to prevent it from even sliding based on the tension that's pulling it. So no acceleration. Not even going to get started. So no acceleration. Now, let's consider the second scenario. In this case, mass 1 is 5 kilograms. Mass 2 is 10 kilograms. The coefficient is 0.6, so there will still be friction in this direction, and the kinetic friction is 0.4. So to determine if it's actually going to move again, we'd make that same comparison. Well, M2 is still 10 kilograms. So based on the math we just did a minute ago, we can know that the tension in the rope is going to be 50 newtons. And the maximum possible static friction would be mu times normal force, which, as we just found out earlier, would be m1g. So mu is, 0.6 times 50. Well, right off the bat, any fraction of 50 is going to be less than friction, is going to be less than 50. So the tension is going to be greater than the static friction. Therefore, it will move. And as soon as we know that it's moving, we instantly shift gears to kinetic friction. So static friction is out of the story. All right, well, let's give ourselves some more room. So now that, let's leave that there. We'll just kind of keep that off to the side, make it small for reference. So that tells us it is going to move. Now we got to figure out more stuff. Now that things are accelerating. Free body diagrams. So for mass 2, it is being held up by 2 strings, tension, and it's being pulled down by its own weight, m2g. And it's going to go down. So I'm going to call downward positive for that object. So we end up with a positive acceleration in that solution. So that tells us that m2g minus 2t equals m2a. The sum of the forces on the second box equals mass 2 times acceleration. All right, so we've got a formula for that. What do we know? Let's plug a couple values in. We know the mass is 10 kilograms, so that gives us the weight as 100 newtons minus 2t. We don't know that, equals the mass again, which is 10, so 10a. All right, put a little star next to that because that's necessary to move. Well, that's as far as we can go with that before we find out what's going on elsewhere. All right, box number 1. Looks like this. There's going to be some kinetic friction that way. There's going to be some tension that way. M1g down, normal force up. Since this normal and weight force cancel each other out, they're going to be equal. So we can I'm just going to sort of skip ahead and recognize that the, let's see, kinetic friction force will then be mu n, which in turn is going to be mu m1g. All right, so we'll just kind of put that there for a second while we consider what direction this thing's actually going to go. Well, if M2 is going to drop, then M1 is going to go to the left. I'm going to call that positive. So the tension that's acting on it, I'm going to say it's going to be tension will be the positive force. Tension minus kinetic friction equals M1a. And again, let's plug some values in. So tension minus the friction force, which is going to be kinetic friction 0.4 times M1, which is 5, times gravity, which is 10, equals 5a. So we got tension minus 4/10 of 50, so that's going to be 20, equals 5a. And the astute observer will by now have picked up on something that I almost neglected to recognize, and that is the accelerations of these two objects are not the same. M2, because it's held up by 2 ropes, and as this rope feeds this thing, M2's, I'll say the acceleration of object 2 is only going to be half as great as the acceleration of object 1. Or I could say it the other way. Object 1 is going to accelerate at twice the rate of object 2. So if we're talking about object 2 here, we're talking about its acceleration. And we're talking about object 1 here, we're talking about its acceleration. So, well, I'm going to put another star right here because that's as far as we can go there. We've got tension, acceleration 2, tension, acceleration 1. We've got 3 unknowns, and we do, in fact, have 3 equations because we know, based on the number of ropes, how the accelerations are going to compare to each other. 3 equations, 3 unknowns. 3 unknowns, 3 equations. So that means we're going to have to start plugging stuff in. It's just a system of equations. Yeah, it's 3, but the algebra is, the algebra is a little bit more cumbersome, but it's not a new idea. So I'm going to choose this equation to sub in right there. So that gives me t minus 20 equals 5 times 2a2. So that gives me t minus 20 equals 10a2. And then we will pick this up, make a copy of it, bring it down here just for reference. So let's see what we can do with that. Oh, look at that. 10a2 and 10a2. How you choose to go about your system of equations is very personal choice. In this case, I already have a term that matches up nicely, so I'm going to just slide that right in there. But I've got positive and positive, so what I'm going to do is basically I'm just going to subtract this entire line, subtract that whole thing. So if I distribute the minus in, I get minus 100. Oh, no. Plus 2t minus 10a2. So if I follow through this, I get 10a2 minus 10a2, so that's 0. I've got t plus 2t, so that's 3t, and I got negative 20 and negative 100, so 3t minus 120 equals 0, 3t equals 120, t equals 40 newtons. Fantastic. One thing down. What comes next? Now let's plug it back in. So we got 100 minus 2t equals 10a2. That's this one right here. 100 minus 2 times 40 equals 10a2. 100 minus 80 equals 10a2. Divide everything by 10. Let's see, 20. 20 divided by 10 equals a2. A2 is 2 meters per second squared. 2 down, 1 to go. A1 is 2a2, which is 2. So A1 is 4 meters per second squared. All right, job done.